Welcome to our channel TeamFilGer. If you're a regular visitor, you have seen the movies of the family. This time it's going to be something different. It's the husband talking about his hobbies at home. So I have something pretty excited lined up, and this is a completely passively cooled home server, which means it's a computer that is going to be completely silent. You might ask yourself, why am I doing this? Well, just look on the right. So what happened was that I was browsing the web and I came across this PC chassis, and I immediately felt like, well, I have to do something with this one. This is exciting. I'm doing this just for the experience of building it, but I actually want to use it in reality in the end. What are the goals? What are we trying to achieve? Like I said already in the intro, it's going to be completely silent. There will be absolutely no moving parts, so no fans, no water cooling, nothing. So only passive cooling, or the technical term that is used here is conduction cooling. When I mean zero noise, I really mean zero noise. I'm going to put this in the room where I'm holding my afternoon naps, and I don't want to be able to hear it. The function that this system is going to fulfill is going to be like a NAS system. So it will have very fast storage, NVMe based, and also some SATA based SSDs. And it will have 10 gigabit Ethernet connectivity, just that I'm able to really pump in 1 gigabyte per second in and out of the system. A second use case is, so I work as an engineer, while doing this, frequently I'm compiling code. So I like to work on a Raspberry Pi actually, which is, how to say, also if you have it in the office, a computer that emits no noise. But compiling on it is rather tedious, so it's a very low power CPU. So the idea is to say I will sit on the Raspberry Pi, use this just for the display, then connect to this machine where we'll have a bit of a bigger CPU and faster storage, and compile over there. So I'm defining as a goal in the beginning that this system is gonna be good enough once I can in a loop compile a Linux kernel on it endlessly, and in a loop just push in and out files onto the internal storage over 10 gigabit Ethernet. So if from a temperature point of view it can sustain that, then I will say the goal is achieved. And I will also say we'll go for running the CPU at stock speed, so just like you buy it, off the shelf, without doing anything, any modifications to it regarding the clocking mechanism. We'll see how far we can get, so maybe we'll need to tune here a little to reduce power consumption, but this we're going to find out as we go. So in summary, that system is going to be beautiful, silent, blazing fast, and cool. Well, hopefully. So today, let's look at the hardware, and we'll start by unboxing the chassis and seeing what we have. So this is the Streacom DB4. The first impression when lifting it up, it is quite heavy. So this is usual for this kind of chassis. So you need a lot of mass to absorb the heat. Another thing that you can see is here on the outside, we can see this pattern there. So this pattern is basically made to increase the surface area on the side. So like this, more surface area means that there is more heat transfer to the outside world. So in the end, what we want is, all the heat from the electronics gets transferred here to the walls, and then from the walls to the outside. This is basically the idea. Another thing that strikes me immediately is the top cover here. This is like plastic kind of thing. I would say this is wasted potential. So I would have imagined that there is another metal part here on the top, which would additionally be used to dissipate heat. Let's open it up. So here is this nice screws here on the side. So we just have 4 of those, which allow us to remove the cover. So there we go. So this is very light, just plastic. So now let's look on the inside. Here we have the motherboard tray. We can see there is mounting of the motherboard is here from this side. So the motherboard is like face down. So the I/O shield points out down in the chassis, and it gets screwed here. So this part, I think we'll be able to just take it out. I will just loosen the screws here. There we go, so it just flips out like that. We're going to mount the motherboard on top of here, so here we can see the 4 threads. It's a mini ITX form factor, so we'll be having only a very, very small motherboard. These lines here are there to put screws through this piece of metal, so we can take some standard 2.5-inch SSDs, for example, put them here against the back and screw them in from this side, so they will be held in place like this. It's very convenient that this can be taken out, so all the mounting can be done outside, and then afterwards it can be inserted again. So here we can see we have 2 slots. So the mini ITX motherboard will have only 1 slot. So this is going to be this one. So there we'll put 1 expansion card. That second slot, I think they foresaw on the chassis in case you want to install a GPU which requires more space. So we could have a dual slot GPU in there. Of course, this one will not be able to cool a high performance GPU. So there will have to be some compromises. So you will need to have something small that can be installed here only. But in our use case, there will be no GPU in there at all. We are going to use the PCI Express slot for something else, but we'll come to that later. Here on the side, we have these black brackets, so they can be removed as well. They are used for multiple purposes. So on the one hand, they can also be used to mount some hard drives on the rear side of the chassis. The other function that they have is, so if we want to have cooling blocks which transfer the heat from the electronic components to the side panels of the chassis, they are there to press those blocks against the outside, the metal part. We have those blocks. They came with the chassis. So here on the side we can insert heat pipes. Those heat pipes will then go to the electronics, and they go here against the wall, and then with those brackets they can be just pressed against the wall. So that's basically the main principles on the chassis. The side walls can also be taken off, so for easier accessibility in case of need. So there is just screws here on the side, but here we go. I'm not going to do that because I don't think it will add a lot of value right now. So this came with the chassis. So this is a block that gets put on top of the CPU. So there's a piece of copper. This one is put on the heat spreader of the CPU. The heat pipes are inserted here, and then this one is put on top. Okay, so here we have this universal mounting system. So we can just open the screws, and here, depending on the socket that we have on the other side, we can just move this and put the other screws. So these are the heat pipes. So basically, the way that those work is, so the idea is to transport heat from the hot end to the colder end. The colder end is at the outside of the chassis. The hotter end is on the electronic part, so for example the CPU. Inside those heat pipes there is a gas. So that gas, when heat is coming in here, it will evaporate and then climb up here. Here on the outside it will cool down and it will actually go back. And that movement of the gas is actually what the mechanism that is used to transport the heat. So then those are getting connected in here. Here we go. This goes on top of the CPU. The CPU in the end will be like this when we install the motherboard. And then the other side, they will go here. So we have the heat pipe here inserted. We can have more than one. And then like this, we can make a connection here from the CPU here to the wall. So it will be multiple heat pipes in the end. So this is the basic principle how the thing is going to work. What the manufacturer says is that this cooling kit is good enough for a CPU with a TDP of 65 watts. Well, 65 watts TDP is a number which does not say too much. In practice, so the CPU, will clock up and clock down, quite dynamically will dynamically like this adjust also the power draw that it has. So like this, it is very hard, I mean, to say that from 65 watt TDPs, if the cooling kit is good enough for 65 watt TDPs, it's really going to work. So we'll have to experiment and see what we find out about this. Okay, then the other package. So here we have a few screws, thermal pads. There is a big thermal pad that's probably going to be used put here for thermal conductivity to the wall. And they also added some thermal paste. Next to that kit, so they are selling also an expansion kit for CPU cooling. So this is this one. So here we have two more of those, including thermal pads. So they are there to connect to the walls again. So the idea seems to be that instead of connecting to one wall of the chassis, we are able to connect to a total of 3 walls on the chassis. Then here we have more heat pipes. So this is there to add also to the CPU. So let's open those up. All right. So if I'm taking back. So this is the one that we had before. So let's say we are doing a heat pipe here to this wall. We can, with that, add another heat pipe to this wall, and with that add another heat pipe to this wall. So this one is going to be here then. This one is going to be here. And this one is going to be here. Then of course we can add more heat pipes, and so like this we can connect to 3 bolts. So here the fact that we can actually move here in this direction or in this direction allows us to adjust them into different kinds of main boards. So one thing that we'll see is, of course, so here, this heat pipe, if there is some electronics here on the side, it might collide. So I will be looking at the motherboard later to see whether we have some kind of problems there. This one we should be rather safe, because in fact it will be like that in the real thing. So this one will be going away from the top side of the PCB. So what else do we have? So here we have additional mounting brackets. These are the same like the ones I showed before inside the chassis. So there's one for each block on the side, so we can add additional pressure there on those. Some more thermal paste. So thermal paste will be important on all the parts, of course. And screws. Then here we have another extension kit. So they call this the GPU cooling kit. So the idea here is to use this with the PCI Express slots that we have in the chassis. So it's similar like the CPU kit, but a bit different. So here we have another of those, a little smaller. So this one would go again here. So this one we would put against the GPU on the extension card. Here we have again the same mounting brackets like we have on the other side. Then here we have another one of those, which allows to connect the heat pipes to the wall of the chassis. And here we have heat pipes again in a bit of a different shape. So in this case, so if we go back to the chassis, so the PCI Express card would be mounted here in this sense. So the heat pipes in this case would be aligned like that. So here we have the block which presses those against the wall, and then here this one goes against the chassis. Okay. So like I said, we are not going to have a GPU in the system. So the PCI Express slot will actually be housing another card. So we'll see, I mean, whether this one will need a cooling kit or not. So we can experiment and find out, I mean, how hot these components will get. However, what might be helpful is, so this kit also gave us another one of those big blocks. So if we compare, so these are the blocks that came with the CPU extension kit. So maybe we can exchange actually and use this also for the CPU to create here a larger contact area with the outside wall and see whether this will help us in terms of thermal connectivity. So that's another cooling kit that I found. This one is a cooling kit for NVMe. This one caught my attention for that project because it works based on a heat pipe. So we have here the lower part here, so this one sits on top of the, or let's say the NVMe sits in here, connects here to the bottom and to the top, and then there's a heat pipe there transporting the heat there to this device. So this one seems to be made for use in an airflow environment. So if you put this into a regular computer which has a fan, you would do it in a way that the air blows through this one, and then like this, I mean, the cooling effect happens. Now, I will try and put this in the system without airflow and to see whether just transporting the heat up here and here this additional surface will already be enough to give out the heat into the air, or whether we will need to mount this also on the wall, I mean, like we do for the CPU and the GPU. In either case, then it gives us a piece of metal where a heat pipe can be inserted there that we can add on top of the NVMe. So in either case, it will be helpful in one way or the other. So then here I bought additional thermal interface material. So these are cooling pads that are used to create a thermal connection between two pieces of metal. So normally you would use thermal paste for this one, but I'm expecting that during the course of the project I will be assembling and disassembling that box quite often. So thermal paste is a one-use thing. So whenever you applied it and you disassemble it, you scratch off the thermal paste and you throw it away. These pads you can actually reuse. So you can disassemble, put them again, disassemble, put them again. Of course they will also wear out at one point in time. I'm pretty certain about this. But I guess it would be cheaper, I mean, to actually use those, I mean, while assembling the system and doing experiments. Now, it is also an interesting question on how well they will perform thermally. So we can with this also then do comparative measurements. Like, I mean, say we apply thermal paste, we do a run or a test run, we apply this one and we do a test run and we see, I mean, at which temperature the CPU, for example, settles. Maybe that makes a difference. So let's see, I mean, how this look like. So I have already one here which I opened before. So let's see what's inside. So here we go. Oh, that looks very nicely packaged. So let's open it up. And here we go. All right, so here is that black part. This is it. So this size here, this is actually made for a Threadripper CPU. So the size here is too big, I mean, for the CPU that we are going to use here. So I don't have experience with those pads yet, so I'm not sure whether I'm supposed to touch them with my fingers or not. So I'll just be using a small tool to move them. And here we go. It's a very fine material that we'll be putting between the metals, and that is supposed to be exchanging the heat. This is another part that came with the chassis. So this is actually a power supply, also a completely silent power supply, so without any fans. So this one is a custom form factor, and how to say, it's made, I mean, to work with this chassis. Here we have the 220 or 110 volt inlay. Here we have all the usual connectors, 24 pin ATX, 12 volts for the CPU, Molex and SATA connectors. So this will go on the back behind the motherboard. So I'll be showing an analysis later to go into more details. As a next step, we are going to look at the motherboard. I chose an ASRock motherboard. This is a server mainboard, and this one has particular features which make it very suitable for use in a NAS system. So let's see what we have in there. So instructions, screws, cables, let's take those aside, we'll look at those later. Here is the board itself. The mounting orientation in the chassis is going to be like this. So the heat pipes that are coming off the CPU, they are going onto this wall, and then we have space for heat pipes to go this way. Well, and then the heat pipes which will go this way, there we already will have the first problem. So we'll have the PCI Express card here, so the heat pipes from here will not easily go on this wall. So what I showed before on the CPU cooler extension, this is already the first thing where we'll have to adapt. Now let's look at the motherboard itself. It's very small. Here we got the standard AM4 socket that is going to house the Ryzen 5600 that I'll be using in that system. We have 4 SO DIMMs. Those are going to hold the DDR4 memory. If you are familiar with building PCs at home, you might notice one difference immediately, and there is no ATX24 power pin on this motherboard. That is due to the fact that in the server space the power supplies are all limited to 12 volts only. So the only power supply that we have on the board is this one here, which is a standard 12 volt connector. It's the same connector that is actually used in a PC to power the CPU. So here it's used to power the entire mainboard. We have a small connector here that is labeled in yellow. So it is good that this is labeled because this is actually a power output connector. This one is providing the power for the SATA drives. So in the SATA connector there is a 5 volt and also 3.3 volts. So in a normal PC it's the power supply that is providing those voltages. On this motherboard the 12 volts are taken from here, are converted by the motherboard, and then are output here. So there is a specific cable that comes with the motherboard which is doing exactly that. This is that cable. So we can see we have here 4-pin connector. This one will go here on the motherboard, and then here we have a total of 6 SATA connectors that we can use to power the SSD drives. So other specific features of this mainboard, so there is a dual 10 gig Ethernet on board. Those 10 gig Ethernet ports are provided by an Intel X550 chip, which is below this heatsink. Next to this there is an additional Ethernet connector which is here. So this is an IPMI connector. Well, it's standard Ethernet, but it uses the IPMI protocol to remote manage that mainboard. This is also a quite typical feature in the server space. So you normally do not have a screen on every computer that you have, but instead you would have an IPMI network which is used to remotely configure that mainboard. Then there is, for debug purposes, a VGA connector here. So it is possible to hook up a monitor, but this is just a very basic output really. So just for a text terminal basically to do some settings. What we see over here is the X570 chipset. This is accompanying the main CPU, and this is basically used to provide the SATA and PCI Express connectivity. Then what makes that board particularly useful for a NAS is actually those 2 little connectors over there. Those are Oculink connectors. So they are also not very common in the home PC space. So those are used to provide either SATA signaling or PCI Express signaling. So you can configure in the BIOS whether on one of those connectors you have 4 SATA ports or you have 1 PCI Express X4 port. And then you can use an adapter cable to either wire up SATA drives or some solid state NVMe PCI Express drives. So for this there is a cable that is delivered with the mainboard. So this is that one. That's an Oculink to SATA cable. One connector here on the side that goes in the motherboard, and we have 4 SATA drives that we can connect here. Let's talk a bit about cooling. This mainboard, being a server mainboard, is made for heavy airflow cooling. So we can see on the orientation here of the fins that it expects that the air is coming like this over the mainboard. So now we're going to put this in our chassis where we'll have 0 airflow, which will mean that so those coolers here, they will of course get hot and dissipate some of the heat up on the surrounding air, but it's an interesting question whether this is good enough. So whether without any airflow, at one point in time the coolers will just get hot and then the component will stay hot. So it will take like 10 minutes for the system to warm up, and then we are in a situation where everything is quite hot. So we might have to consider, or I might have to find a solution to actually replace those coolers with something that is adequate for the chassis. So but first I'll do a measurement to see what happens here really. As a next step, let's look at the CPU. So we're going to be using a Ryzen 5600X. I chose the Ryzen 5000 because it's probably, in terms of power consumption versus compute performance, the most efficient CPU that you can buy for a home system in the moment. So that's a 6-core 12-thread CPU, quite powerful. Let's insert this one in the socket. We have here the AM4 socket. So basically, so we open the handle here, then we take the CPU out here, orient it, find the correct orientation. So there is a little marking here on the side which helps to orient it correctly. Then we just lay it flat down here, and we put that handle down and click it, and there we go, we got the CPU installed. As the next step, we are going to be looking on memory. So this motherboard will take up to 4 SODIMMs. So I got some crucial SODIMMs from Micron, 2 times 16 gigabyte, running at 3200 megahertz double data rate, so 1.6 gigahertz. In reality, it's a CL22. I read online while I was researching for the board that this board is a bit peculiar in what kind of memory it accepts. So I specifically looked up the official list of the vendor, what kind of memory modules are accepted. So I took those because they are on that list. Now let's look at the cooling concept again. So here the memory, it has no heat sinks. So again, if we have a usual chassis, we would have airflow from here. Maybe that's already good enough to cool the memory. I'll have to find out whether the memory stays within temperature bounds when operated in a non-airflow scenario. Otherwise, I also need to think, what can be done to keep the memory cool enough. Now let's take the cooling kit of the chassis and just see how that would look like. So I'm not going to mount it including thermal paste and everything, just want to show the mechanics. Here we got that copper block, so this is going on top of the heat spreader of the CPU. Of course we would need thermal paste now here before we put that, and then a second layer of thermal paste on top of that. Right, then, so we have seen before, so this is the heat pipe assembly. This heat pipe here, okay, that is going out and that does not seem to be colliding anywhere, so we'll be able to use that heat pipe to transport heat to that side of the chassis. But if we're looking at this, if this is supposed to go on that side here and it goes down, this one is colliding with the memory. And if I'm going over here, this one is colliding with that heatsink, and then here will be a PCI Express part, so this is also going to be in a problem. So that CPU extension kit, as it is sold with the chassis just alone, is not usable in that configuration. As a next step, we are looking at the NVMe carrier that we're going to be using. So this is a NAS system, so we want to have a lot of NVMe storage in there. Here's the carrier card that is going to do that. So first impression here, this is actually quite heavy, so that's quite interesting to see. So they made a very big effort there with the cooler already. We have a PCI Express X16 connector that just goes to the motherboard. And then here we have 4 NVMe slots to install 4 NVMe cards or NVMe drives. So as we can see, there is no PCI Express switch on that board. So the function of this board relies entirely on the fact that this X16 connector here can be split up into 4 X4 connectors. So in order to operate that card, we need a motherboard that supports on that slot what is called PCI Express bifurcation. So the way to split up that x16 into 4 x4 slots. I checked out the specification of the main board, and they say yes, they can do that. So then I would assume that this will just work. So we see that the main board and the CPU can support PCI Express Gen 4 actually, but this one here is a PCI Express Gen 3. So also all the NVMe drives that I'm putting over there are all Gen 3. So Gen 3 on 4 lanes means 4 times 8 gigabits. So 32 gigabits, I mean, for each of those leads to a theoretical bandwidth of like 4 gigabytes per card. That's more than enough. So here we have a fan, so that we are going to disable again, either by removing the plug, or I check already, so there is a connector here where we can switch off the fan. So we definitely will have this switched off, and then we'll see what we can do to keep the cooling intact. The NVMe drives that we're going to be using are the latest Samsung. So this is the SSD 990s. They are rated at 3.5 gigabytes per second read speed here. So which is in line, I mean, what the PCI Express Gen 3 can do. I checked the datasheet, and if they are under full load, so one of those has peak power consumptions of like 4.5 watts. So when we have 4 of those operating in total, so let's say we are at around 18 watts that this carrier is consuming with the drives alone. So that's quite some heat to dissipate. So here we have terminal pads that will transfer the heat from the NVMe drives here to this frame. The frame is actually quite heavy, it's quite well done, but we can see it's made for airflow. So since we are going to leave this disabled, so we'll be running again without airflow, of course. It's an interesting question. If I just put this up, is this going to be good enough to just dissipate the heat there into the chassis, or do we have to do something else to keep the NVMe carrier cold? We are having a total of 4 of those NVMe drives which are going onto that carrier, and well, a 5th one that will go on the main board. So let's just open up one just to see. These NVMe drives are 1 terabyte. They are going to be installed like this here on the carrier. It will be 4 of them, so we'll be having 4 terabytes of storage on the carrier and a 5th NVMe on the motherboard, so for a total of 5 terabytes of NVMe. As the last part that we'll be looking at today is we have 4 SATA SSDs, also 1 terabyte, so this is also from the Samsung. Here we can open those up. So this is the motherboard tray. So the idea is that those will be mounted here onto the back, and we can see that it lines up quite well with those holes. Probably it should go like that, so we can have 1, 2 SATA drives mounted here on the back, and probably I will just put the additional 2 on top of this. In the first part of this video series, now we have seen all the components in the system. So let's take a brief look of what is going to be next. One important piece of information that we need will be the power consumption of the system. So the question there is whether the power supply that was delivered with the chassis is able to provide enough power for that computer. A second interesting question is, so like we have seen, all the coolers on the main board, for instance, are made for cooling in an airflow environment. So a big question will be, how will they behave when we have a scenario where there is no more airflow, like in the DB4 chassis? As a first baseline, I have prepared the system here. So thanks to Movie Magic, it happens instantly. There I'm using a standard cooler to do baseline measurements to see at which temperatures the components will settle, and then this will be used as reference when running the system in the actual conduction cooled chassis. I already mentioned the thin client that we are going to use in that project, so expect also a video on how we are going to build up this one. I have not yet spoken at all about the software architecture and the storage architecture of the system. So we know for the storage architecture that NVMe and SATA SSDs are going to be used, but there are a lot of open questions that still remain. I'm looking forward to continuing that video series, so I'm sure it will be an exciting ride. If you got interested in that, please subscribe and hit that bell down below.